Okay, I didn't draw this very well, but above your XY plane, you got some function. Got all this curvature and stuff. It's just one of these, a bit bigger to give it room to do some waviness and stuff like that on top. Maybe part of a quadrant function or something like that. And we've seen this picture. You have your partial derivative. So maybe above a smaller region, maybe, well, okay, let's just take this part. And let's say, and I'm projecting that to the wrong place down here. This projection line's a little more sensitive. But actually that one is okay. This one should only come to here. So now we have a slice of this graph here. Okay, so this slice we can bring out here and turn it around so we can see it. And maybe it looks something like this. Well, I don't want that much curvature. That was an accident. Board kind of grabbed the chalk. So let's make it a little straighter because it's supposed to be a small interval, so maybe there's a little curvature. Traffic lights are working for me, nothing else. Okay. But there we have it, okay? And we could take a small increment here. And this thing is practically straight on this small increment because it doesn't have room to change direction much. So now let's take this out here and just change the scale a little bit so we can label it and just spread out the x values. Okay, so where did we start here? Well, we started with some interval, like maybe from A to B. And here is some x naught. And that's going to correspond to a point here. We have some x naught, y naught, here. So, keeping in mind that y naught isn't going to change, we have an x naught here, and we have sort of an x-axis along here. Just staying with me? See where this is in the picture? And for all points here, y equals y naught, x varies along this line here. Okay. Along points there, the y naught is the same at every point. The x value changes obviously because x is in this direction. And this is supposed to be parallel to the x-axis. I did a really bad job of making that parallel. Okay. Screw that up. That thought, just because of the way I drew it up here, and I was a little careless. Okay. So here we have the picture, and now we have a small increment. X naught here, x naught plus h here, where h is the width of this that's written small. If you're looking at it in the video, it might be a little hard to see the H here. Although YouTube does a pretty good job. Of high definition, so you probably can read it. But anyhow, we understand now that this distance is h, this x naught, this is x naught plus h. And what do we have? We have this side is f of x naught, y naught. This side is f of x naught, y naught plus h. So now we do what I call the fundamental triangle. Not a universally applied term, but it should be. And eventually, many years after we're all gone, somebody's going to adopt it, and it's going to become universal. And we'll be famous forever. Although we'll be dead. Okay, it's going to be hundreds of years. Well, anyhow, got this triangle up here. There's a run, there's a rise, there's a slope. So I'm going to bring this triangle out. That is h. The rise, and I didn't leave myself nearly enough room to write it, but I'm going to write it anyhow, is just, we're going from this, in this direction. The run is plus h. The rise is the difference here, like you measured on the first day. But now we have it in symbols. Then we've got to be able to write the slope. So the rise is what? F of x naught apparently I can't bring myself to really focus on what I'm writing. Y naught is constant, of course, because it's x that's changing. It's f of x naught plus h. Y naught. Why do we have y naught there? Well, because this is a function of three variables, and we said let y naught be constant. Why not? Okay. Now we have then f of x naught plus h y naught minus f of x naught y naught. So the slope, which is the approximate derivative, that's what the derivative means. The derivative is the limit as h approaches 0 of this slope. In other words, it's the limit as you shrink this thing down toward x naught. Limit as h approaches 0 is going to give you the instantaneous slope at this point. This is a big deal because this is the approximate derivative. I say it's the approximate rate of change of f of xy with respect to x, because x is what's changing and causing the change in f of xy at the point x naught, y naught, which is I don't have room to write it somewhere. Okay? And I could say this is the approximate partial derivative of f with respect to x, because the derivative is just this limit. Okay, so big deal here. Partial derivative of f with respect to x at the point x naught, y naught equals the limit of this as h approaches 0 of f of x naught plus h y naught minus f of x naught y naught over h. And then, of course, partial derivative of f with respect to x at any point x, y. You just, instead of using x naught, y naught, you use x, y. So right there is your partial derivative of f with respect to x at a specific point x naught, y naught. Now you can also do the partial derivative of f with respect to y. Okay, so what you do there is you hold x constant, and you're going to have a line straight across here. And in the plane where x is constant at x naught, y naught, now we have y changing, and we can write the corresponding expression for y. Didn't really leave myself room to do that. I would like to get it on here somewhere. Okay, so I'm going to take this picture here, and I'm going to move this picture over here. And I'm going to make a similar increment here. Okay. And I'm not going to draw this picture. From this is y naught. We'll call this y naught plus h. X naught remains constant. Y changes from y naught to y naught plus h. And we get another expression. We have another color. Yeah, okay. Use green. Okay, so that now this implies, through a bunch of stuff here, it's just a complete mimic of this, except that now, instead of adding h to x naught, we're going to add h to y naught. We get exactly the same expression, but now it's y that's changing. So we get the partial derivative of f with respect to y at, almost throw the y there, x naught, y naught. There we have it. Okay. So, I'm going to go a little further with this. If we know the values of these partial derivatives, then at this point we know the direction of a tangent vector in this direction and a tangent vector in this direction. Okay? Tangent vector just going to be, let's say, in this direction is going to be j, because you go in the j direction. plus k multiplied by this partial derivative. Because, well, I guess it's worth messing up another board now. So let's try to manage this a little bit. I have a better place to put my chalk out anyway. Okay, go a little further here. And let's see if we've got, yeah, board still visible. Okay. If we take this picture again, or just, let's say, okay, well, what we've done here is we've essentially sliced the graph of our function f of xy with the plane y equals y naught. The plane y equals y naught, well, down in the xy plane, y equals y naught. It's just like a vertical line. If you reorient your axis, so y is this way and x is this way, it's a vertical line, but it's a line parallel to the x-axis to a point x naught, y naught. The plane is just right above and below that line, because if you write y equals y naught, you haven't restricted z. Z can be anything. So any point above or below this line satisfies y equals y naught. So there's your plane. Now you should be familiar with that because we've done some planes. Okay? And similarly, this plane defined by this purple line from negative infinity to infinity is the plane x equals x naught. So we've sliced our graph of the function with the plane x equals x naught, which gives us some curve. Now I'll make that curve a little more extensive. I'll keep it colored. So here's an auxiliary x-axis. I think all this is z prime axis. And here's the point x naught. And here's the graph. Make sure we get the right slope when we get here. Of f of x, y naught. Meaning x can vary, but y is fixed at y naught. So this is the intersection of the plane it's the intersection, the plane y equals y naught with the graph of f of x, y. We have our blue section corresponds to this. And actually, according to our colors over here, this would be yellow if you want to keep this consistent with this. And here's the blue trapezoid. Here's your little increment of width h. Take the limit as h goes to 0, and you get the slope of this thing. Now I'm saying with the vector, something's breaking apart. Okay, vector. The slope at this point your slope is a partial derivative with respect to f. Like we said here, and you want to digest all this, make sure you really understand. The universe is getting back at me for all the traffic lights having worked. Okay. Well, the slope of this vector, if you wish. Is this. Okay, so let's take this vector and bring it down here. This could be any vector, but this is a vector tangent at this point. And bring this vector to this point, it'll be tangent to the curve. Abusing the language a little bit because a vector can't really be tangent. Really we'd say, okay, there's a line here parallel to this vector, but I'm still going to treat the vectors if we just move it here and call it the tangent vector. Vector can be really anywhere. So if I want to get a tangent vector, I'm just going to let this side be I, and I'm going to let this side be partial derivative with respect to f, with respect to x, partial of f with respect to x, at the point x naught y naught times the k vector. And that vector will have the direction of the tangent line. So if I wanted to put that vector in here, it would be a yellow vector parallel to the x-axis in this direction, but rising a little bit if this in fact rises. Okay, so it'd be a vector here. Well, all that is, if we take our little friend here, we have kept y constant. So here's our xz plane, and here's this segment, or this segment, and the slope at this point is a partial of f with respect to x at the point x naught y naught. This point being x naught y naught in the y plane, this height being f of x naught y naught, and this height being f of x naught plus h y naught. At this point we have slope equal to this partial derivative, which is approximately equal to the slope of this side of the object. So that should completely orient you to this picture. So now when I talk about this, I can say, okay, well, whatever corner is x naught, y naught, the slope of this side is approximately equal to the partial derivative. And since the use of the slopes and functions of one variable being equal to derivatives, hopefully, and understand how the derivative is defined for a function of one variable, we've essentially reduced this to a function of one variable here. We've got a partial derivative, and from that partial derivative, we get a tangent vector. And now I'm gonna suppress the x naught, y naught. You just understand that at whatever point, if you want a tangent vector to this surface in the direction of the, well, within the y equals y naught plane or whatever, within a fixed, within the plane defined by a fixed value of y, we get this tangent vector. And of course, you understand why the slope of this vector here is equal to the partial derivative. Because the length of this side, the run is 1, because that's the I vector, and the rise is, K is a unit vector, rise is just a partial derivative. So the rise divided by the run is a partial derivative divided by 1, which is just the partial derivative. Okay, well, this tangent vector is real important. I'll say it again and again. We're going to use it again and again. Okay, then we also have what's a tangent vector in this plane? Okay, before we go on, I'm going to ask you to sit there and digest this a little bit and tell me what would the tangent vector in the plane x equals x naught be?